So what we're going to do in lecture 3B is Ataberk will introduce you to the labs and FPGAs, what you're going to do the entire semester in the lab assignments. And then we're going to also, you can reduce the.
Yeah, I did.
Okay, you did. Okay. Basically, a little bit about FPGAs also. You may not understand everything about the introduction to FPGAs, since we're going to start covering combinational logic tomorrow. But FPGAs are execution engines that you're going to use, real hardware that you're going to use in your labs. Any questions before we begin? I saw a hand somewhere, but maybe, okay, yes. This mic is not working, right?
Is this working?
How about that one?
Is this not working also?
Somehow that is working.
Okay, it's working.
Okay, you can only use one mic at a time. All right.
Should I get started then?
Yeah,
okay. So thank you, Onur, for the introduction. I'm a first-year PhD student in Professor Mutlu's group. And I'll start with logistics for the labs lectures. So the on-site labs will take place in these rooms that you can see over there. You can find more information about these in the DDCA course catalog webpage. And we will also hold online sessions for the labs. And we will share with you how, like, the details on how to join those meetings later. And these lectures are taking place at these time slots, and you can learn more about these in the course catalog webpage. Yeah, I'll talk about grading. So you will get, have to go through 10 labs, and you will get 30 points in total. And we will put the lab manuals online before each lab, before each session. And you can see them on this link over there. Now, about grading policy, you will be evaluated based on your in-class performance, and 70% will make up that in-class evaluation. And you will be also evaluated on the mandatory lab reports that you need to submit. And that will make up to 30% of the point you get from a lab. And there will be a 1-point penalty for late submissions of the reports. And we expect you to finish the labs within 1 week after they are announced. So if we announce a lab next Monday, you will have time until next week and in the session that you selected in the model, basically. And you can use, you could use your grades for labs from past years until yesterday night, I think, on model. And this was okay, this is not updated, but some of you did. And for questions, you can send us emails to this mailing list, or you can use the Moodle forums that we will create per lab, per assignment. Okay, any questions about the logistics? No, cool. So what we will learn in these lab lectures. So these will focus on design space and trade-offs in these 3 layers. So you're familiar with this transformation hierarchy from previous lectures, right? And we will understand how a processor works underneath the software layer. And to do that, we will touch on implementation details at these 3 levels of the hierarchy. And we will gain hands-on experience in digital circuit implementation. Yep. In the end, you will learn how to make trade-offs between performance and overall complexity of your designs in your hardware implementations. And you will learn this by gaining hands-on experience on hardware prototyping, on field programmable gate arrays, or FPGAs, which we will describe in the upcoming slides. You will debug your hardware implementation to find out the bugs in your designs, and then you will learn how to express hardware using hardware description languages. And you will be familiarized with the hardware design flow, the fundamentals of hardware design flow. And you will also learn how to use computer-aided design tools to develop designs on FPGAs. So let's continue with a brief introduction to FPGAs. And FPGA is short for Field Programmable Gate Array. And this is an FPGA chip. They usually look like this. And what you see here is an integrated circuit also, or a chip. And these chips come in boards like these, with a lot of different modules embedded on the board, and they serve different purposes. So FPGAs are versatile, so they can be used to enable many different applications. And how are they so versatile? And the answer is because they're reconfigurable. So when you have an FPGA, you can program it after you've bought it, after it's been produced and comes out of the fabrication. You can still reprogram it to implement another hardware, different hardware. And that enables essentially the versatility. And in the lowest level, FPGAs have many simple reconfigurable functions spread across the chip. And we have a means of connecting these functions together in a reconfigurable way. And we can also connect these functions and the connections to the input and output, physical inputs and outputs of the FPGA device itself. You'll see how FPGAs compare against other integrated circuits, and this slide Onur showed you in the previous lecture, so I'll reuse it. And here, the other types of integrated circuits could be CPUs, processors, general purpose processors, graphics processing units, which will be covered in the upcoming lectures, and application-specific integrated circuits. So FPGAs would belong here if you were to put this scale down here. So to the left, as we go towards the CPUs, we get more flexibility and it's easier to program. As we get towards the ASICs, we get higher efficiency. So FPGAs compared to ASICs will be easier to program, develop your designs on, but since the ASIC is essentially specializing, is using the whole silicon area to specialize for a single application, and we won't be able to be, FPGAs won't be as efficient as those because we're trading off some area for reconfigurability. And compared to CPUs and GPUs, we will be more efficient because we will be able to specialize for a single application compared to this general purpose CPU that can run at tons of different workloads. So we will look at where exactly FPGAs are used in today's systems. And starting with this example, this is Microsoft's project Brainwave. It's a deep learning platform for real-time AI inference on the cloud. And in this platform, Microsoft is using the FPGA to implement what's called a neural processing unit to accelerate deep neural network inference, and they use this in computer vision and natural language processing applications on the cloud. Another example is Amazon's EC2, F1 instances. Amazon essentially has these computers on their clouds available for people to rent and use them for a temporary time. Yeah. And interested customers will just rent these servers out. Yeah, you can think of it as a customer as someone that wants to run a lot of workloads on a lot of FPGAs, but they don't want to also purchase a lot of FPGAs, so they will just use Amazon's EC2 F1 instances to run their application, run their workloads, get their computation done. And from the bioinformatics area, this is another use case. This Illumina's Dragon platform, yes. It is an genomics analysis accelerator. It accelerates tasks like mapping and alignment, sorting, and variant calling, which are critical in genomics analysis tasks. And more FPGA-based platforms have been developed before for, again, genomics analysis. Researchers from Safari collaborate in collaboration with researchers from Bill Kent University developed Gatekeeper, the first FPGA-based alignment filter. And this accelerates a key stage in DNA read mapping process, which is pre-alignment filtering. And then they developed Sneaky Snake, which is an improved version, I would say, tackling the same problem again. And these works have been published on bioinformatics conferences, as you can see here. And you can see many more insights into how FPGAs are used to accelerate genomics analysis. And this primer paper has been published on IEEE Micro. Now, FPGAs are also used to accelerate other types of workloads. In this work, the authors accelerate weather modeling, climate modeling solutions, basically. And here they demonstrate FPGA-enabled near memory computation can accelerate genomics and climate modeling applications significantly. And this is the system they're using in this work. And they show that this system can improve performance from 5 to 27x and increase energy efficiency by 12 to 133x compared to a IBM Power 9 CPU, compared to a computer, basically. Beyond accelerations, we use FPGAs to develop infrastructures that we ultimately use to test different devices. In this case, we developed SoftMC to test DRAM chips, DRAM devices, as a flexible and easy to use platform. And we have used it in many prior works to develop better understanding into DRAM reliability, security, and performance issues. And you can find the source code of SoftMC online on GitHub on this link. Yeah, a more recent version of the same platform has been used in recent works to develop further understanding into RowHammer and how RowHammer mitigations work, basically. And an even older version of the same framework, same platform, has been used in the first RowHammer paper to uncover that RowHammer existed in a widespread manner across devices that are available to public back then, and also discovered many other insights about RowHammer. These are the recent works that I talked to you about in previous slides. Yeah, and FPGAs are also used not only to test DRAM chips, but also other memory technologies, like in this case, NAND-based flash chips. And here you see a system, an FPGA platform that has NAND flash chips attached. And we use this to develop better understanding into reliability characteristics and of NAND-based SSDs and perform error characterization. And we use FPGAs to develop prototypes for new architectures as well. So in this work, we developed PyDRAM, which enabled us to do real system evaluation of two in-DRAM computation techniques, copy and true random number generation. And PyDRAM is also open source, and you can find it on this link here. And we also developed an FPGA-based prototype for Metasys, which is an open source, again, metadata management system. And here we evaluate the system, perform a limit study to understand the bottlenecks associated with general metadata management systems. And this is also open source, and you can find it in this link. Now I'll move on to the overview for the lab exercises, and we'll start by looking at our FPGA board that we will use in the labs. So you can see that there are many inputs and outputs or peripheral devices that we can use that are placed along the in different parts of the board, right? And these are all connected to the FPGA chip that's on the middle of the board. So you'll use this FPGA at the end of the exercises to develop your first 32-bit microprocessor, and you will download it and you will run this processor on this FPGA. And it will be a small processor, but you will be able to execute any program with it, pretty much any program with it. And each week we will have a new exercise, and some of the exercises won't require FPGAs, and we will get to those. And you're encouraged to experiment with the board on your own. So if you need a board, but you don't have it at one moment, you can ask us. It's unlikely that you will get a board because we have like limited number of boards, and I think we have to distribute them all, but ask anyways. And this is something you can take as a challenge, but you cannot destroy the board by programming it. If you do, that will be the first, I think, in the history of the lecture. Yeah. But yeah, don't try to destroy it. Yeah, okay. So first lab, in the first lab, we will draw a basic circuit, no FPGA involved. So comparison, is an operation we use in software programming commonly, and because we usually want to know the relation between two variables. And we will compare two electrical signals in the first lab. and we will output another electrical signal that encodes the result of the comparison. So if it's equal, we will output 1. If it's not, we will output 0, for example. Right? And yeah, no FPGA programming involved, but you can try it out later. In the second lab, you will implement another common operation. It's called addition. We will add 2 1-bit numbers, and then we will design the circuit that adds 2 1-bit numbers, and then we will reuse this to perform 4-bit addition. And reusing hardware modules is really important in hardware design because you can build on the simple things that you have, build confidence on that, that they're working correctly. So we will make sure that the 1-bit adder is working correctly, and we will use that adder multiple times to create another module. And we will implement this design on the FPGA board this time, and we will use the input, we will use the switches as encoding the operands of the operation, and we will output the result of the operation using the LEDs. And in the third lab, we will output the results on the 7-segment displays that you see here on the board. And you will learn how to encode the values that need to be displayed on this 7-segment display. And you will learn to do that basically. In lab 4, you will develop your first finite state machine, and this is going to simulate the blinking, harsh turn signals, and you will blink basically LEDs. And to maintain that state for the finite state machine, we will use memories. And then in the lab, we will also change the blinking speed of these LEDs. In lab 5, we will implement what's called an ALU, arithmetic logic unit, or ALU. This is going to be the first step towards implementing your very first microprocessor. And ALU is an important part of the CPU because it is responsible for doing these computations like addition, subtraction, multiplication, and logic operations like AND and OR. In lab 6, you will simulate the design that you developed in lab 5, and you will comprehensively verify that it's working correctly. And you will resolve problems that exist in your design if they do. In lab 7, you will write assembly code. For the MIPS ISA. Here are 2 examples of the same program. Basically, this is written in C, something like C, and this is the MIPS assembly. You can think of assembly as writing code using only the instructions of the ISA and not something high level like C. And this code will be doing, you will be using this, you'll run this program on the CPU you develop in the end of the lecture. And this will be doing some image manipulation tasks. In lab 8, this is going to take 2 weeks. This will be covered in 2 weeks, and you will learn how a processor is built in just 2 weeks. Complete your first design of a MIPS processor, and you will then run a snake program, which will develop this beautiful pattern on the 7-segment displays. And in the last lab, I think, you will improve the performance of your processor that you developed in 2 weeks. And you do that by adding new support for multiplication and bit shifting operations. Okay, any questions about the labs? Okay. You know, right? Yeah. So the question is, do we need a Windows machine to program the FPGAs, right? And I don't think you need it. Basically, you can use either Windows or Ubuntu machines. And if you're attending the labs on site, you can use the computer rooms or the computers in the lab rooms to use Vivata, basically. But it's really tricky to get the software we need running on a Mac. I think I haven't tried it. Okay, any other questions? Okay. So yeah, we talked about what FPGAs are briefly, but this didn't supposed to be an animation here. Sorry. So we call that FPGA is a reconfigurable hardware substrate, and where it's placed in this flexibility efficiency spectrum, right? So they are reconfigurable, and that's why they can support being efficient and also are easier to program compared to ASICs. And now we will try to understand how that's possible. So how is the reconfigurability implemented, but at a very basic level. So this is an overview of an FPGA. You can see that it's made up of logic blocks, switch blocks, and interconnects, and some I/O blocks. And these are all reconfigurable, meaning that we can freely route from one logic block to another logic block using the interconnect. There are two main building blocks in an FPGA, lookup tables and switches. So here's a different depiction of the FPGA that we looked at in the previous slide. Here on the left, you see how lookup tables and switches are distributed on the FPGA. And in a lookup table, we have what's called a multiplexer. This is a digital circuit element that we will cover in the upcoming slides. And there's something called configuration memories, some flip-flops or memories to store the state and manage the state when needed. And if you look at the bottom right corner here, this is the distribution, I think, in an area for the interconnect and the configuration memory and action logic, meaning the multiplexer. So you can see that the interconnect takes up a huge space here. And yeah, we will be freely able to route from from the output of a LUT lookup table to another lookup table's input. And this way we implement functions in the FPGA. So how do we program a lookup table? This is an example lookup table. It has a 3-bit input, and that's why it's called 3LUT. And you can see that we have the input bits here in red, and output will be 1 bit. And what this does is it picks from one of the boxes. These boxes are a single bit. Basically, each one of these is a single bit. And to do that selection, it will look at these input bits. So based on what the input bit encoding looks like, we will select one of these. And this is called the data input. This is called the select input. And if the select input is 0, and there are 3 bits here, so it's 0, 0, 0, we will pick this first box. So whatever stored in that storage unit or data input will be output through this multiplexer. So if it's 1, we will pick the first one. If it's 2, 3, 4, you get the idea. And we say here that a 3LUT can implement any 3-bit function. And we will see over an example, and you will probably understand why that's correct. And we will try to implement a function that will output a 1 when there are more than when there's more than 1 ones. Okay, let's see. When there are at least 2 ones in a 3-bit input. When at least two of the bits are set in a 3-bit input, this will output a 1. So if you were to program this in C, you could write something like this. Basically, we're iterating over all bits of the input. Here, what this operation is doing is it's selecting a bit, and then when we shift it by 1, we will, in the next iteration, select the 2nd bit, and in the last iteration, we will select the 3rd bit. And if the bit is 1, we will increment this count. If count is larger than 1, we will return 1. Another way to implement this in C is like this. So we are enumerating every case where the output will be 0. So there will be less than or equal to 1 set bits in the 3-bit input. You can see it here, like if it's 0, there are no set bits. If it's 1, there's only 1 set bit. If it's 2 and 4, there are only 1 set bits because of the binary encoding. And we will return 0 in that case, and otherwise we will return 1. So programming this in a LUT looks more like the second implementation in C. So we have already enumerated what the select input bits can look like here. And what we will do is just move this return value to these boxes such that it will return the correct value. It will implement the correct function. Here you can see that we will put 0 in this first box, 0 in the other 2 boxes because there's only 1 set bit in the input. You can see here. And here there will be one because there are more than one set bits. And we'll go ahead and fill up the remaining boxes. And this is how we implement a function basically in a lot. Any questions about that one? It's not too complex, I think. Okay, cool. So how do we implement more complex functions? How do we implement the processor? There are many lookup tables and switches in an FPGA, and this diagram I showed you is just a simply a very small part of the whole FPGA chip. So we have a lot of small lookup tables. They can individually implement different functions, and then we can reconfigure the interconnect to make them work in unison to implement a more complicated function. In modern FPGA architectures, just so you get the idea of the scale, you use many lots, thousands of lookup tables with 6-bit inputs. So we can implement any 6-bit Boolean function using one of them. And there are megabytes of distributed on-chip memory to hold state, to store state, maintain state. And there are hard-coded, by hard-coded we mean that not reconfigurable specialized blocks that are responsible for interfacing with high-speed memory devices and low latency, high bandwidth off-chip I/O devices, and many more, basically. And even sometimes a general purpose processor will be integrated into the same FPGA chip. And here's an example for such a chip. This is the Xilinx Zinc UltraScale Plus. And you can see here that on top of the programmable logic, we have 2 CPUs, a memory controller, some accelerators for cryptographic workloads, and some other like units that are responsible for other parts of the system. Okay, so we will talk about the advantages and disadvantages of FPGAs once again. So we talked about how FPGAs enable reconfigurability, and that's why they're versatile, but it comes at a cost. We will talk about the advantages first. So since we can implement any algorithm directly in the hardware, directly in the FPGA hardware, we're not bound by any ISA, so we can specialize for that algorithm, and this enables high performance and high energy efficiency compared to CPUs and GPUs. Compared to GPUs for some workloads, let's say. And this has also low development cost compared to a custom hardware design, because when you think of it, FPGAs are something I could have here and program it immediately using my laptop. But to develop Cerebrus wafer scale engine, I need to do more, basically. And compared to ASIC, this is much easier to develop. And it has also a short time to market because it's reconfigurable in the field. So if I have an FPGA, I can already implement a new design on top of it. And it's usable and reusable for many purposes because of the same reason. So imagine I have an outdated hardware that's running on many of the systems that I have. I want to update it. So what I do is just reprogram the FPGA with the new hardware. Disadvantages are compared to the wafer scale engine or ASICs. These won't be as efficient and as fast and as power efficient, basically, because we're sacrificing some of the area for reconfigurability, whereas those ASICs don't. And reconfigurability comes at another cost. It also has significant latency overheads. So you will rarely see that FPGAs exceed some high clock speeds. So it's really hard to see an FPGA that has a higher than 1 gigahertz clock frequency compared to your CPUs, which reach in these days around 5 gigahertz clock frequencies, right? Okay. So we'll talk about how we program FPGAs now. We talk about them being programmable, but we don't know how to program them. So we'll use what's called computer-aided design tools for that purpose, because FPGAs have many resources, and there's no way for us to program them manually. So imagine you have millions of lookup tables, and how do you route one output to another input on your own? You can't. And these computer-aided design tools are interested in answering these questions. So how can we represent a high-level functional description of the hardware structure using FPGA resources? This is describing the translation process from the Verilog code to FPGA resources. like lookup tables and switches, and select which resources to map our circuit to. Okay, I know that my circuit will require this many lookup tables, but where exactly are those lookup tables located? Where should they be located? And optimally configure the interconnect between the selected resources. So how do I lay out the lookup tables, and how do I route the connections in between them so that I get the best latency area, different constraints. And then finally generate a configuration file so that the FPGA is able to understand and reconfigure itself based on my design. So this is another look at the design flow. So first we start with the problem definition, and then we have to convert this. We have to find a solution and convert it, express it in terms of a hardware description language. So this can be Verilog or VHDL. So you will use Verilog. In this course, there are many other hardware description languages, but these are the rather popular ones. And your task will be this. So you will write Verilog code to solve a problem. And then there are steps like logic synthesis, placement and routing, and bitstream generation that I talked about in the previous slide. And this is automated by the software tool that we're going to use, Xilinx Vivado. And finally, you will use the bitstream that's generated by the Vivado tool to program the FPGA and run your own hardware on top of it. Yeah, more about Vivado. Basically, it's a software tool that helps us throughout the FPGA design flow. So you can see here, we have run synthesis button, implementation button. These are responsible for the last 3 stages of that flow in the previous slide. So we just need to press buttons for those, and it's automated. And it provides multiple tools to simulate, for us to simulate our designs and understand the bugs and solve them. And it also provides drivers for your computer and a nice interface for you to easily program the FPGA board using USB cables. And they're installed in these rooms, so you can use those. And finally, we have a tutorial on how to, this will briefly introduce you to writing Verilog code and following through the FPGA design flow steps using Vivado, and then finally download the bitstream onto the FPGA to run your hardware. This demo is about a simple keyboard. It's a simple hardware that in the end of the course, you will be easily able to develop. Compared to the microprocessor, this sounds a bit more lame, I would say, but yeah. And link to the source files of this keyboard you can find here. So if we, I think we have time. So maybe I can play this video and then I'll voice over when in the key section. So is it playing right now? Yeah, in this demo, you will see how we program a BSS3 FPGA board with this demo, the simple keyboard demo. So this is the Vivado's user interface. You will press this create project button to create a project, and then metadata about the project, like project's name and where it will be created. You will fill these in. And then press next, right? Multiple times. And you get to this window, the part selection. This is where you select the FPGA so that the tool is able to understand what the FPGA is going to program and do the flow steps correctly. You will select this part. You don't need to memorize it. We'll provide the part number to you in lab manuals and in a written document. Now we're downloading the source files for this keyboard demo on this website using the link provided in the previous slide. So there's a zip archive here that you can find when you visit the website, and you download that. Again, you can view this video anytime you want, so you don't need to memorize every step. So adding source files using this button, and then we select design sources, right? And then we find the files with the Verilog extension, .v extension. Those are the source files, and then we will add them to the project. Now we will also add another source file. This is going to be this file has an XDC extension, which is short for I don't know, but it is defining how we map the inputs and outputs of the top level of the Verilog design that we have to the physical inputs and outputs of the FPGA. And once we have those, we can go ahead and click this button, generate bitstream, and this will basically schedule the tasks for Vivado that needs to be done for us to get the bitstream. So it's running the hardware design flow right now. It won't finish this quickly, but when it finishes, you can plug in this micro USB cable here to both power on the FPGA and then to connect it to your machine that runs Vivado and where you have the bitstream located. Once you connect this, Vivado will understand that the computer is connected to an FPGA board. Yeah, this is what you should see. If you don't see that, please let us know when you power on the FPGA board. Yeah, you connect this USB cable to be able to, oh, this is for the keyboard, yeah. So you'll open the hardware manager and then click this button, open target, auto connect, and then you will load the bitstream. You will load the bitstream, yes. Now, yeah, you do that by selecting program device. Yes. Okay, now the device is programmed. Now it's it is the demo program loaded on the FPGA. And here we connect to the FPGA over that USB cable using a serial interface. And once we press the buttons, we will have some output here, outputting the ASCII codes for those buttons that we pressed on the keyboard. So this keyboard is plugged into the FPGA for this demo, in case you missed it. Okay, this was it for the demo. And we covered these today. I don't know if you have any questions. This is where the slides end. If you have any questions, I can take them now. Okay. Oh, there is a question somewhere. Okay, yes. Do you get a link for the software? Yes. Yes, we will share those details with you. Over Moodle, I think. We will find a way. Yes. Oh, yes. Can you repeat? Sorry. What exactly do you mean by in-class evaluation? Oh. Yeah, so what in-class evaluation means is you will have to show your work to the TA, basically. And you have time until next week's session to do that. Yes? Yeah, you can do that. Once we distribute those FPGAs, you can take them with you. The problem is you will have to share it with your partner, and you will need to find a way how to do that.
There's also a question on Zoom.
Yeah.
So do the students taking the online labs receive a basis 3?
Maybe you can read it.
Maybe, yeah. Or do the students taking the online lab receive a basis 3? No, yes, they do. They can come, we will announce pickup dates, FPGA pickup dates for everyone to come to the ETZ building and take an FPGA for.
Okay, any other questions? Can people hear me? Okay, I can use yours then.
Yeah.
Thanks, Ataberk. Yeah, no problem. Let me make a, yeah, you just make Ataberk. All right, Ataberk is going to be the one of the head TAs for the labs. But before we finish, let me show you that if you didn't understand anything about, for example, the lookup tables, we will start covering things like this tomorrow. So you will know exactly what this circuit is, for example. It's a lookup table, as you can see. It's also called a multiplexer. It basically selects one of the inputs. And you will see that tomorrow in the combinational logic lecture. And we will build an entire processor starting from components like this. Actually, we will start a little bit lower level. We'll start with the transistor and then build up these logic gates. But this is called a multiplexer that's used as a lookup table. So you will see it tomorrow. I'll see you tomorrow. Take care.